Okay, hello everyone. This is video one of two videos. I'm trying not to go over 15, definitely no more than 20 minutes. The second video will be much shorter. This video is section 4.5, where I'm also going to have you look at the notes for 4.6 because it really goes hand in hand in this section, and it's not that long. So I'm gonna have you look at both videos before Friday, and I'll have a worksheet for you, a fun sheet for you guys to work on pertaining to just these two sections. Okay. All right, so 4.5 is the dimension of a vector space. And although we are doing now this flip model, it's still important for you all to still read the book and go through the book, skim the book. I would probably look through that section first, then look at the video, and hopefully everything will make sense, sort of highlighting the main points. All right, so let's get started. Okay, just some basic definitions. So dimension, we've talked about dimension, but now I want to give you a formal definition since we now know what a basis is. And so the formal definition of a dimension is that the dimension is of a vector space is the number of vectors in the basis for that vector space. Okay, so that's how we determine the dimension of a vector space. That's the first definition. And so the second definition, if a vector space V has a basis with a finite number of elements, i.e. n elements, then we say that that space is finite dimensional. And if it's not finite dimensional, then we call it infinite dimensional. Okay. And so just some examples of finite and infinite dimensional vector spaces. We have dimension of R3, right? And so we know that the basis for that, here's the standard basis. And so for R3, the dimension is 3, okay? And I'm sorry, this is the notation for dimension. I think I mentioned it later in the video, but that's the notation for dimension. So for Rn, the dimension is n, and that's the standard basis for Rn. We talked about that. Now for Pn, again, that's all our polynomials up till degree n. Because we're taking into account our constant function, then the degree of P sub n is actually n plus 1, okay? And so infinite dimensional, so those are finite dimensional. Infinite dimensional vector spaces are our functions of reals. This is our continuous functions, and these are our differential functions, which we may talk about. I don't know if we're going to get too much into it. Probably won't get too much into that in terms of examples, maybe later on in another section. But for now, I just wanted to give you some examples of infinite finite dimensional sets. Okay. So some more things before we actually just do some examples. If V is n-dimensional, then the basis for V, so this is very, very important. If V is n-dimensional, and you probably maybe guessed this because, you know, we talked about in class reducing, if we have these vectors and trying to find a basis in a certain vector space, reducing it down when we do the REF, then if we can reduce it down to the identity matrix, then it spans that space. And so if V is n-dimensional, then the basis for V has only n vectors. Okay, so that's an important fact to remember and to know. And so from that, we have a couple theorems. One, if V has a basis, so if this basis is B1 up until Bn, then any set in V containing more than n vectors must be linearly dependent. And that sort of makes sense, right? Because if we're saying only if we have in R3, at most 3 vectors, has only, the basis for that has only 3 vectors for R3, right? So if we have a basis, so if V has a basis, then any set in V containing more. So if we have a set of 5 vectors in a R3, then we know that it has to be linearly dependent, right? Okay, hope that makes sense. And then the other theorem, all bases of a vector space V have n elements. Okay, all bases of a vector space V. If V, again, we're talking about if V is n-dimensional. Okay, so all bases of a vector space V have n elements, right? Because we know basis isn't unique, right? Because we have the standard basis, but we also have other bases that we could use for the same space, okay? All right, so you may want to stop this and write it down and then follow along. And so here's an example. So find the dimension and basis for the subspace. So we have S is spanned by these three vectors, okay? And so I put dependent there, but that's actually, we're going to find that out. The first thing you need to do is put it in the matrix and then row reduce. So make sure you check my work. If there's anything that's not clear or not correct, if I made an error, make sure you let me know. And so it row reduces down and REF to that. We have two pivot columns. That's how we know it's dependent, right? Because there are only two pivot columns. And so we have a free variable. And remember to go back. And so this is another reason I didn't state this in class. Remember, this is an REF, right? If you recall, when we first started, REF isn't unique, correct? So if you thought, oh, I can use these vectors, well, someone else who does a REF differently could have different vectors, right? So that's another reason why it's important to go back to your original vectors, to go back to the original matrix to get your vectors that create your basis, okay? And so since the first two columns are pivots, then the first two columns from our original matrix form our basis, okay? And so in fact, although this is a span, S is the span of these three vectors, in fact, the basis, we only need two vectors because one of those vectors, the third vector, is dependent on the other two, okay? And so since we only have two vectors in our basis, then the notation, so that means the dimension of S equals 2, okay? So hopefully that makes sense. If not, you can go back over this example. All right, so the next example, find the dimension and basis for the subspace. All right, so here we have H. And so we wrote this out as the linear combination, pull those vectors out. And so we want to know, are these vectors linearly independent? Well, here, since it's two vectors, we can just look to see if they're scalar multiples of each other, or you could also put in a matrix and row reduce, or use any of our other theorems that lets us know if we have dependent versus independent. So they are independent, and so therefore they form the basis, and so the dimension of H is equal to 2. Okay. All right, the next example. All right, so make sure again you check my work, because I have to go back over this example again because I had made a mistake. So make sure you check my work to make sure everything's right. Make sure you do this on your own to verify that you get the same answer I get. And so are these vectors linearly independent? All right, so again, we have right here that linear combination, and we row reduce to REF. And so we get the 3 column, the first, second, and the fourth column are pivot columns. And so that tells us that, I'll put on another page, yes. So that tells us that we have what? That are the vectors linearly independent? That tells us no, right? Because we have a free variable. And so thus the basis for H is those 3 column vectors, going back again to the original matrix. Okay. Well, now let's talk about extending sets to form a basis. Okay, I'm sorry, I'm not gonna. Okay. Theorem. So let V be an n-dimensional vector space with subspace H of V. All right. So any linearly independent set S contained in H can be expanded. Any linearly independent, that's important, set S that's in H can be expanded to form a basis for H, okay? And in fact, and hopefully this makes sense to you all, the dimension of H is less than or equal to the dimension of V, right? Because we know for our basis, it has exactly n vectors, all right? Because it is our dimension of our vector space. Okay, so let's look at this example. So we have extend the linearly independent set to form a basis for P2. So in S, the set S only contains 2 polynomials. We know in P2, recall in P2, the dimension, remember for polynomials, the dimension is n plus 1. So in P2, the dimension is n plus 3. 2 plus 1, which is 3. And so that means to form a basis for, so that means for a basis for P2, we need 3, right? We need 3 vectors because that's the relationship between our basis. The basis and the dimension is the number of vectors in our basis. And if we already know our dimension, which we do for this example, then we know how many vectors we need in our basis. Okay, so it's a couple things that come into play in order to extend. So I could ask you, so to extend the space to form a basis for a certain subspace. All right, so again, recall for P2 the standard basis, right? So that's the basis 1x and x squared. So to extend S, we need to use the standard basis for P2. Okay, and so remember in class we represented our elements in S as vectors when we did the example with the polynomial. So we're going to do that here. And so I just rewrote S on this page. And so as vectors, you can make sure you double check my work. Those are the vectors of S. All right, -1, 0, 1 and 3, -2, 0. Again, I just rewrote it since we're in this new slide. Rewrote the standard basis for P2 is 1x x squared. And we can represent those as vectors as well, right? And in fact, they're the vectors here. 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? Isn't that cool? Okay, I thought that was cool. All right. So now, in order to extend, we put our 2 vectors that we have in S and the column vectors of our standard basis in a matrix and wrote in REF and put it in REF, okay? I did not, because of space and time, I did not write all my steps, so you can stop this video and row reduce and then check to verify to make sure you get my same answer. Although again, since it's in REF, it's not going to be unique, but your pivot columns should be the same. No matter if those numbers might not be the same in REF, but the pivot column should be the same, okay? So in fact, we have 3 pivot columns, all right? And here, so that tells us that this third column, because remember the first 2 were already our vectors in S, right? And so we needed to add, because we needed to extend or expand S to form a basis. And in fact, the pivot columns tell you that. And so that is represented by this third column, which is represented here by, because you always, again, go back to the original matrix. So for our basis for this, in extending it, it is the first 2 vectors that we already had plus that third vector there that we found in REF by using REF and the standard basis for P2. So therefore our dimension of S is 3, which is, we already knew that because we knew that we were talking about P2 and we know the dimension is n plus 1. Okay. You might have to stop this video and go back, and that's fine, to make sure you fully understand that. Okay. All right, so the basis theorem. So now let V be a p-dimensional vector space where p is greater than or equal to 1. All right. And so I made this note right here. This is the useful theorem when the dimension of a vector space is known. So when you know the dimension of your vector space, you can use this theorem and it comes in handy. So if you know that you have some p-dimensional vector space where p is greater than or equal to 1, then any linearly independent set S with p vectors is a basis for V, okay? And that sort of makes sense, right? Because if it has p vectors and it's linearly independent and it's in V, then it's going to span that as well, right? If it's linearly independent, it's going to span that space and therefore it's a basis. And so that's one fact that we know. And then another fact, any set S and V with p elements that span V is a basis for V. So basically what this is saying is that if you know the dimension of the vector space you're looking at, the 2 conditions, remember the 2 conditions for a basis is that the set of vectors have to be linearly independent and they have to span, right? That's that subspace that we're referring to. And so if we know the dimension of our vector space, then this theorem is saying if you know the dimension, then you just basically need to show that the set of vectors are linearly independent or that they span. So it's not like with the basis you have to show both of those exist. Here it's saying if you know what the dimension of your vector space is, then all you need to show is that those vectors are linearly independent if they equal your dimension, right? It has to be p vectors in that subset that we're talking about, right? Okay. All right, so that's a good fact that we can keep in mind. here's another nice property that help us simplify our life. So it's easy to find the dimension of the null of A and the dimension of the column of A if you realize the following. So remember when we were talking about when I asked you to find the null of A, you row reduced and your free variables were basically that became your span, right? And so the dimension of your null space then is just the number of non-pivot columns of A. And the term for that, because you'll see, is nullity. Nullity refers to the size of your null space, okay? Which is the same thing as saying what's the dimension of your null space. The size of your null space is saying how many vectors, and that's the same thing as saying the dimension, all right? So we use dimension, but it's basically looking at the size of your space, which means how many vectors are in that null set. And you know that by it's the number of non-pivot columns. Whereas the dimension of column of A, that represents the number of pivot columns of A, okay? And that's called the rank, which we'll talk about in 4.6. So that's called the rank, and that's equal to your dimension of your column of A. And so therefore, putting this together, we can say that the dimension of the null space of A plus the dimension of the column space of A, because again, it's the non-pivot columns plus the pivot columns. Well, that equals the total number of columns, right? Okay. So in other words, rank plus nullity equals total columns of A. Okay. And this is the last slide for this video. So I'm a little over 15 minutes, but I'm gonna stay under 20. Find the dimension of A and the dimension of the column space of A, okay? And so here we have the matrix A, and this should look familiar because I think we've used the same matrix in our notes before. However, I'll still leave it to you all to row reduce it down, and so I skipped that step, but the final version of when you row reduce, well, REF, again, the numbers could be different, but the pivot columns will be the same. So we see here, that we have a pivot column in the first and third columns, and that means the other two columns are our free variables or our non-pivot columns. Therefore, the dimension of the columns of A is 2, and the dimension of the nullity, the dimension of the null space of A or the nullity of A is 2. And if we add 2 plus 2 together, we get what? 4, which is the number of columns. Isn't that sweet? I love it. Okay. So I'm going to stop this video and then I'll start the one for 4.6. Like I said, it's not very long and it's actually bring it together. We're just talking about rank and looking at something a little different, but it's really along the same lines of what we're doing here. Okay.